Okay, we are back here again for the last session. Well, the next two talks are from our members of the Calculus project. And the first one is Victor Milewski, that he's a PhD student working on multimodal structure representations.
All right. Hello, everyone. So I'm Victor, and I'm going to present my latest work, which is what can we learn from the structures found in visual and language data and the correlations. And this is, well, we show here a bit of an opinion paper. We highlight some of the different areas where these kind of structures are worked on, and we do a small scale experiment to show a bit of these correlations. So what do we talk about in this talk? So when we talk about structures and interactions in the physical world, there's a lot of interaction between objects, humans and objects, and between humans themselves, which are very easy for humans to comprehend and understand, while they are rather difficult for computers and machines to automatically recognize and understand. So if we look here at the image in the top right, we see the guy here on the skateboard, and for us it's clear that the guy is performing some sort of trick in the midair, and he's maybe jumping over something, and we directly understand this. But for a computer to recognize this, the objects are now not even attached to each other. So how does the computer then know there's an interaction between them? For a computer, it's just as similar if there are two objects next to each other with no interaction at all. So this makes that understanding of these structures already very complex. But yeah, for humans, this is very natural. And if we go to a second example, to the room, we have here a space with a lot of elements. We have a television, it's above the fireplace, as we so often see in American homes. And then we have a couch there next to the coffee table. And there's all these common patterns that humans, in this case, designed our room in this structure. But there's always a common pattern and a structured organization in how we organize things around us. And we believe if we can comprehend these kind of structures, that hopefully our models can improve by using this. So what are we going to talk about? I will give first a short overview of some of the language structures we looked at. Then I go over a couple of the visual structures, and then we perform a small-scale experiment to investigate some of the correlations. So I think most of us are familiar with language grammars and grammatical structures. And and these grammars are there to guide us on how our language and sentences are formed and constructed. And there's two main grammars that exist and definitions that are used, which are the constituency trees, which we see here on the right, where we group our words and sentences or words into phrases, in these noun phrases, and we hierarchically expand our sentence into these phrases up to words to group them into pairs and groups. And it creates this nice hierarchical pattern for our sentence. While in the dependency tree, we measure or create direct relationships between words, and we see the direct interactions on what the effect of words have on each other, which still creates a very distinctive tree pattern. And the useful thing is we see with dependency trees, they're very far developed now that they are large data sets that create these universally across many languages. So it's a very easy pattern to analyze over many languages to see these common structures over the entire human speech and text. So then we go to another language structure we look at here, which is the scene tree. And this we proposed in an earlier paper, where we try to discover if there's structure or tree-like structure or grammar-like structures in between objects and regions in images. And for this, we created a mapping from a dependency tree structure on top of the image structures on the objects there. And so as you can see here, we have here on the bottom a sentence with a dependency tree. So the black lines visualize the dependency tree of this sentence. And in that sentence, we have all these colors. And these colors are elements and phrases that are aligned with these objects. So we have an older man, and we see here the blue box for an older man. And in the sentence, we see here the pair of the 3 children and the older man that are exploring among the rocks. So we have here a relationship described and an action described between those children and the men. And here we have then all these objects in the image. I cannot even find my own pointer now. So we have these people in the image and all the boxes, and they represent that same, we want to represent that same structure. So by traversing our dependency tree, and every time we encounter one of these colored phrases, we add a node to our scene tree and expand the scene tree so we have this tree-like structure for our image and the objects there. The next structure we look at is the scene graph, and it's the most well-known version of it is from the visual genome data set, which is a very large, extensive data set where they aim to have a better explanation of images. Since if you only look at objects, they said that's very hard to discern between 2 images, but once you incorporate the relations and attributes, the representation becomes much more unique. So their motivation was that such a graph should allow for better grounding of concepts and formalize the representation. So what we end up here in such a scene graph is all these orange objects, orange to pink, and then the green blobs are the relations between all those objects, and then then you still have the blue attributes. So it's extremely dense, a lot of concepts, and no really rules on how this is structured. So it's really a free-form graph, and everything is allowed. So it's very hard to discern any structure or organized structure in it. And they did that by incorporating, allowing humans to create many free-form sentences. And from these many sentences, they extracted all the objects and relations mentioned there to collect all these graph structures for the image. And they merged all those tiny graphs into one big one. So now we have a look at the structure of the physical world and of visual data. And here we look more at how humans perceive the world. And what was discovered is that humans have 2 types of processing over the physical world, and that is semantic knowledge and episodic knowledge. So you can imagine if you are in a kitchen and you're looking for the bread. If it's your own kitchen, you know exactly where your bread is stored, and you go to the fridge and it's on top of the fridge, for example. But if you're in somebody else's kitchen, you have never seen the kitchen before, but if you have to search for bread there, then you use your semantic knowledge, and you know the bread is either stored in the bread box or maybe in the freezer, and you can very directively search for that. So through these search tasks, these different types of knowledge were discovered by experimenting, by allowing humans to search through these environments. And here we can see that in the image as well. You might expect that people start looking through the center of the image for a mirror, But what people tend to do is they focus mainly on this area above the sink, because that is where they expect a mirror to appear in our bathroom. And so this kind of structure and organization of all these elements, this knowledge creates some form of common patterns of what we expect in our physical world, which can construct some form of grammar. And these kind of grammars, they seem to extend over all types of domains and areas. So here I show an example where we can separate our furniture into this constituency tree-like structure, where we have these phrases for the legs and the phrase for the sitting of the chair. And we can extend it to roads as well, where NVIDIA even created a nice small grammar to generate new roads for their simulations. And so they can generate roads from that. And we see it again for our room structures, where people were here asked to place items in a room or design a room. And they always started with these central phrases. So here the toilet phrase or the sink phrase, and then you have the anchor object, so the main object of that phrase, and around that the essential items are placed, like toilet paper and the mirror. So this is also very interesting work by Melissa Faux we looked at. And so now what we want to investigate if there is some correlation between human processing of the physical world, of that visual data, and how we process data, since there's both seems to be some grammar-like structure present there. And another motivation for that is that from these exostatic, I cannot get the word out, the EEGs studies, they found that there's a similar brain response when looking at inconsistencies, these semantic and semantic inconsistencies in these types of data. So if you see a semantic error in your sentence, or a semantic error here in an image where you see the hairdryer in a forest, then the brain causes a similar activity in your brain where the processing takes place. And this happens across many more modalities even. So we created a small data set where we have a lot of these structures available. So we have object annotations in our image, we have captions present that are aligned with that object, those objects, and we have scene graphs present. So we can analyze all these different structures I mentioned. And then we can compare the distances in those trees and graphs between objects to distance between the bounding boxes in the image. And then we compute the representational similarity analysis, which is, so it's the similarity matrix of all the pairwise distances, and then we compute a ranking correlation over that. So, and what we see here is that for all of our different structures, we get a positive correlation between the structures in the graphs and the distances in between the objects in the images. And the first thing we see is that both the language structures in the top two rows, the trees are, have very similar performance. So you might expect that maybe in a constituency tree it might be further apart, since the dependency tree has more direct connections, but no, both get similar performances. And these language structures perform worse than the other two, but that might also be because there's way more words that cause a bit of noise, and with all the determiners and extra words that are not needed for visual representations. If we look at the scene tree, we get a much better correlation, since that's, which is as expected, since it's more direct aligned to the image. by removing by just focusing on the head nouns of the sentence, we get a more flat and more correlated structure aligned with the image distances. And for the scene graph, we get very high correlation. While the scene graph is generated directly from the image data by describing it, it's also very dense and there's many relations. So you could expect that some of the distances in the graph might appear further than they are actually in the image, or shorter because there are so many pathways through the graph. But no, it appears that they are very correlated here. So that brings us to our final discussion and some open questions that are still there. So as we see, there is this correlation between our physical world and official data and these languages. And we've seen in previous papers that, or previous talks today and yesterday, everybody is interested in generating layouts or looking at generating new combinations between objects. And our model needs to understand this correlation between the two. So how can our data-driven studies help better in that? And maybe we need to, we propose to look into more organized structures for our visual data, and maybe that by looking together with psychologists into how humans process the physical world, maybe we can create a better rule-based system for our structures, so we can find better correlations and discover what causes these structures. What came earlier? Did the language structures influence how we see the physical world, or maybe the other way around, because how the physical world is designed, it's shaped our language grammars. I think we think there's an entire world to explore here that might further aid our discovery and understanding of these models. And as a final note, I want to show that some of our models already have apparently some of these semantic or episodic knowledge. So here we see some clip extractions where we ask for certain keywords. So we see here a surfer and we ask for shoes. While in the water, the surfer is not wearing shoes, but still the model is capable of looking at the correct area. And it is able to find clouds in a cloudless sky. And even the actions like grabbing and standing, it knows where to look at. So the model has learned some of these structural capabilities and this semantic knowledge, but how did it learn this and what did it learn? And yeah, hopefully in the coming years we can discover more about this. So thank you for your attention.
Thank you, Victor. So, do you have questions? Okay, well, you can think about it. So, I have a question about what do you think, if it is a good idea to try to induct this structure in the current visual models or multimodal models, or just scale them more?
Yeah, it's an interesting problem, right? Because with the scaling more, we hope that it learns and captures more, but we don't know if it's actually learning and understanding the world better, or that it might just remember more of what it has seen and maybe correlate it better. So I think we shouldn't be too harsh in saying, oh, you have to follow this grammar, because you might limit your models too much there. But maybe some guidance in how it should organize its representation spaces, maybe disentangle some of its representation spaces to how it learns elements. or discern between the different layers of the transformers where it should store certain information. I think it can help in both understanding our models and maybe it might improve.
Okay. Any other question? No? It was pretty clear.
Right.
Thank you, Victor.
Thank you.
Well, now we have Maria Trushka. She's a postdoctoral researcher, and she's working mainly on text-based control for editing images or scenes. So,
yeah. Hello. Okay, so the title of today's work is text-based control for image manipulation. And here, the aim of our work was to work with relational structure of language and to use also geometric aspects of the visual data in order to obtain an anticipatory method that can work well for text-based image editing. Now, the idea behind the text-based image editing is that we can assume that we have an image, like how you see here, two cats sitting on a bench, and we want to change it using a caption, two cats sitting on the sofa. And in this case, we want to replace the bench with a sofa while keeping the cats in the same position. Now, this task is quite popular, so there are already numerous methods that are proposed for this problem, but they have some current limitations. Usually the background, they have a problem to preserve properly the background, and here through background we understand all the information that is not related to the captions. For example, the cats we consider also as a background, so it's something that should stay unaltered. And also they have a problem to edit images using long or more complex prompts. Yeah, here is an overview of the current presentation. I'll briefly present the method that we proposed for these two limitations, and then I'll start talking about the experiments, the setup, and then the results. Now, about the